Okay. And then I'm gonna start sharing my screen. So do you hear me? Do you see my screen?
Yes.
Okay. So if you remember, we said for any reactor that we want to, any process that we want to design, the first type of unit operation that we have to design is design of the reactors, where the chemical reactions occur. Okay, so this was the first step. And the second step we said is about separators. It could be distillation columns, extraction columns, absorption, desorption, whatever that you have in the process. Okay, so this was the second step in design of a process. But after you design a reactor and you design your separator, then you need to design your heat exchangers, or in other words, heat exchanger network. Okay, because of the limitation of space, my shapes are not really circular, so I hope you accept it. And after that, after you design heat exchanger network in the process, you have to think about utility. You have to design your utility system. Okay, and it is one extremely important part of any process. Okay, so what does it mean? What is utility? When we say utility, we are talking about vapor, we are talking about water, and we are talking about, of course, mostly we are talking about cooling water, but it can be also wastewater and effluents, whatever. Also electricity. Oh, what happened? That's my. Sorry. Also, we are talking about electricity. Electricity. Okay. So this is the discussion of today is mainly about this section, about design of heat exchangers and utilities. We are going to cover these two sections. Okay, why they are important? Because in any process, so depending on the reactors and separators, you end up with different streams. There are streams that they are that in fact they are traveling between different equipment. Some of them are hot streams, some of the streams are cold, and this kind of uh, situation of having cold streams and hot streams really brings the reason to design a heat exchanger network. So when we say heat exchanger network, usually we are talking about um, a, a kind type of heat exchanger equipment where two process streams exchange heat together. For example, let's say uh, we have reaction A that is converted to material B, okay? But if in another stage of the process, you have C that has been converted to D, okay? And now at the end, you have one stream, and let's say stream B, Stream B, for example, is at, for example, a temperature of 100 Celsius, and is going to be, and after the reactor, it has to be cooled down to, let's say, 50 Celsius. But stream D maybe, for example, is at a temperature after the reaction is at a temperature of, let's say, 30 Celsius, but is going to be heated to reach 60 Celsius. And you know that when we talk about the streams, so each, in terms of heating, so you know that delta H is always equivalent to m dot Cp delta T. So the enthalpy, the energy that you require to heat up a stream is a function of um, um, mass flow rate, specific heat capacity, and the delta T. And sometimes, for example, for the case of the course of today, we show capital Cp, large heat capacity, which is in fact a multiplication of mass flow rate by a specific heat capacity. So when you have these two streams like B and D, and one of them wants to be heated to 60 Celsius, another one was to be cooled down to 50 Celsius, you know that we design a heat exchanger, for example, a shell and tube heat exchanger. Uh, one stream, let's say B, for example, enters shell of the exchanger, and then after is cooled down, exits or discharges from another side of the shell, and stream D, for example, can enter a tube a tube bundle at inlet temperature and then go out. So we design a heat exchanger usually in order to maintain this heat exchanger, this kind of heat exchange. And you know that the governing equation for a heat exchanger is UA delta T log mean. In other words, the total heat that is exchanged inside the heat exchanger is a function of overall heat transfer coefficient. We show it by U, which is the coefficient this coefficient is a function of heat transfer coefficient of the cold stream, hot stream, also conductivity, thermal conductivity of, for example, tube material. But this A is also very important. This is the total surface area inside the heat exchanger where the heat is exchanged. And this delta log mean is average is the logarithmic average of the temperatures inside the heat exchanger. So I hope you are remember how to design a heat exchanger. So this type of heat exchanger is the topic of designing heat exchanger networks that I have shown by yellow color. In other words, when you design your process and, for example, you do your uh, process simulation, you have identified your streams. So you have one stream, uh, let's say here's inlet, here's outlet. So you have one streams that they want to be cold, and some streams that are cold and they want to be hot. Okay, so after you identify cold streams and hot streams in a process by a specific technique that we are going to discuss very briefly today, you design heat exchanger. For example, you say this stream, let's say this is a stream 1, stream 2, you have a stream 3, and a stream 4. So then you say, for example, one heat exchanger is required to match stream 1 and stream 4, and you call it, for example, heat exchanger 1. And you have one heat exchanger to match stream 2 to stream 3, you call it heat exchanger 2. But maybe, depending on how you design, you end up with uh, condition that one extra heat exchanger is required for one given stream to have further heat exchange. So then you end up with a heat exchanger, for example, number 3, where stream number 1 and stream number 3 is matched. Okay, so design of this heat exchanger network is a subject of heat integration in process design, including in biomass conversion. So there are different techniques. One technique is by pinch technology method or pinch analysis that today we are going to discuss. But so far, I'm just giving you this introduction that uh, when we talk about heat exchanger network in a process, we are talking about process stream to process stream heat exchange. But let's say that now you have one process stream. For example, let's say a stream A that a stream of the reactant A that we discussed. Let's say I'm going to show you here. This stream had at the beginning, let's say stream A, at the beginning was at 25 Celsius. Okay, but it had to be at 100 Celsius before chemical reaction to produce reactant B. But due to some estimations or restrictions in process, which is the kind of advanced work, you cannot heat up this stream by another process stream, which is, for example, hot and is required to be cooled down. So here for this one, you have to define a specific boiler, for example, or a specific heater, okay, in order to heat up stream A. So when you use a specific heater, uh, uh, which is which supplies the heat by vapor or by electricity or by any other method, this kind of heat exchanger, we call it utility heat exchanger. Okay, because this process stream A, for example, uh, was heated by, for example, vapor. For example, we have a vapor in the unit, and one line of vapor is used to heat up stream A. Okay, so when you use vapor to heat up stream A, this kind of heat exchanger um, is a utility heat exchanger. Okay, so uh, when we say that we have to design a utility system, in fact, utility system is the system where you design, you identify or you determine how much vapor, how much cooling water, how much electricity, how much whatever else in terms of utility you require to heat up or cool down a process stream. Okay, so that's the utility system. So these introductions I'm giving you because then it will be easy for you to follow the course. So imagine that anyway, you have one process that is well designed in terms of reactor, separator, heat exchanger, network, and utility system. Okay, but let's say, let me show you here. Let's say you have one process, we call it process one, and you have another process, we call it process two. Similar to the case of a biorefinery and a pulp and paper. Let's say process one is the process that already exists, like a pulp and paper company. But process two is a new biorefinery that you want to design beside your pulp and paper company, okay, in order to take the advantage. So if you want to really make a very good design, a very optimized design in terms of energy consumption, minimum energy consumption, minimum material consumption, minimum production of waste and effluents, minimum generation of greenhouse gases. If you really have this idea, so that at the end you have a sustainable process, okay, you have to again have uh, that kind of attitude in process design for integration of the two units. Let's say, for example, you have already process one, and process one is generating a lot of vapor. Let's say uh, high pressure vapor, medium pressure vapor, or low pressure vapor. Okay, so if you have process one that already produces vapor, so to design process two, if you need vapor, you don't need to, design a new boiler system, for example, because already process one produces some vapor and you can use it in process number two, and vice versa. Maybe uh, process one, like for example, pulp and paper, requires some water, so it is demanding some water, so we have to add water. But process two, which is your biorefinery, will generate some water due to the depends on the process. But imagine, let's imagine that process two produces water. So the water that you produce from process two can be used in process one. So you are integrating these two processes. And same thing in terms of energy. In terms of energy, maybe some streams in process one are hot, and you can use those streams in process two. So it depends how your process is. For process one, process. So I gave you all these introduction to tell you that when you design a biorefinery, uh, uh, beside reactor performance, beside separators performance, um, at the end, energy is very important. Usually, biomass conversion processes are energy intensive. Okay, especially if you have, for example, gasification, if you have pyrolysis, if you have combustion, whatever. So you have to always find way to minimize energy consumption. So by giving this introduction, which was quite lengthy, I want to now talk about the course, what we are discussing, so you can easily follow up what we say. Chapter 9 is about um energy efficient processes or heat integration of processes. In French, we say efficacité énergétique et intégration des procédés, with the application for biorefineries. Okay, so the objective of the course today is again is to really understand the importance of having a energy efficient system. In other, when we say energy efficient, it means minimum consumption of energy. Again, when we say minimum consumption of energy, usually we talk about utility section, right? Because the other energies are supplied by other process streams. In order to reach a kind of development durable, sustainable development, okay? So in this context, we are hopeful that at the end you understand the principal techniques in process heat integration and how it can be used in order to make your process energy efficient, or in other words, your process uh, is following a very efficient integrated heat consumption. So uh, it's about the problem to cook. It's not important. You can follow it up. Already I discussed about this slide. So we are talking. Imagine that we have, uh, um, for example, a pulp and paper process. In the pulp and paper process, we use wood chips, water, and chemical products, and you want to use cellulosic fibers or cellulosic materials products. Beside it, we want to make a biorefinery in order to make biofuels and bioproducts from lignocellulosic biomass. So, in order to match this process together, in between, uh, as I said before, you would like to really make a good integration so that, for example, you can take advantage of uh, water, vapor, and other streams between two companies, between two processes, so that the cost of the process at the end is minimum, and in terms of efficiency, it is efficient. Okay, so when we say sustainable development, what are the conditions for having a sustainable development? Conditions de durabilité. So ideally, when we talk about sustainable development, we don't want to have any any fossil fuel consumption. We want to have zero energy fuel consumption, fossil fuel consumption. Okay, and as I said several times today, we want to have an energy efficient system so that process is uh, benefits from a heat integration situation, and uh, we have the best situation of heat exchangers with minimum utility consumption. In this regard, also, we would like to have a process that is optimized in terms of water consumption and minimum production of wastewater. So as you will see in the course in our course today, water is a specific stream because water is a utility stream, so you can use water from a utility section of the process, for example, to cool down your streams. As well, water is produced in the process. So, for example, you know that if you have a combustion process, you make vapor, and if you condense it, you make water. Or in some other chemical biochemical processes, to some extent, water is generated. So, water is something very interesting, and that's why when we talk about process heat integration, we have to also have a look at integrated consumption of water, because water uh, comes from two sources, from utility and from the process itself. Anyway, so the other condition for having a sustainable process is that we want to have less and less and less uh, generation of greenhouse gases, GES, greenhouse gases. Okay, so if you want to reach these goals, what we have to do, we have to optimize our vapor consumption, our water consumption, and also we have to find a relationship between all these streams and how at the end we can minimize emissions to environment. Okay, so after this important introduction, in my opinion, is very important because the topic is quite big, and I really want you to look at some references that I have provided in the Moodle, so you can really follow up. So you can really follow up and learn more and more. But that introduction was very, very important, so you understand what we are talking today. If you get lost and you don't follow what we are discussing today, it is useless to continue in the course. So, uh, talking about process heat integration or energy efficient process, one of the most important tools that are used in process in engineering is called pinch analysis, or in French, analyse de pincement. So pinch or pincement. So if you just with two fingers grab your skin, in fact you are pinching. This is pinching. Okay, you will see why we call it pinch. So this pinch analysis is very known technique in order to have a heat integrated process. And it is, if you learn pinch analysis, in my opinion, uh, you will acquire a very important aspect of process engineering, because uh, energy consumption is a huge topic in process engineering, and people who know how to apply pinch analysis to make process integrated in terms of heat, they will be at a good position in their company or in their future workplace. So, what are principles in pinch analysis? Again, pinch analysis is a tool in order to make process heat integration. So it is a tool that we acquire to identify process to process heat exchangers and utility to process heaters and utility to process coolers. Okay, so in this process, in this methodology, streams are defined in two categories. We have um, streams that are source of energy. We call them heat source streams, and we have streams that need to be heated. So they require energy to be heated, and we call them sink source energies. In French, source is the same, but puits is the equivalent for sink. So in other words, in pitch analysis, we classify our streams in two categories. One category are heat source streams that they have enough energy and they are like a donors. So they are, or in other words, they are suppliers of energy in the process. And sink streams that they need energy, so they are demanding energy. That's why we call them sink, because they don't have enough energy. We have to give them, we have to supply them with energy. So heat source streams and sink source streams. Okay. So by identifying heat source streams and sink source streams, usually we combine these streams into specific curves. We call them Cool composite or composite curves, we combine all heat streams in just one stream and all sink streams in one stream, and then we move on with the methodology. Okay, let's see how it looks like. Imagine that in your process you have two hot streams. Stream one is going to be cooled down from 200 to 100 Celsius with a heat capacity of 20 kilowatt per Celsius. So when this CP is in fact a mass flow rate multiplied by specific heat capacity, just to clarify. And stream number two wants to be cooled down from 150 Celsius to 60 degrees C. And you have also two cold streams or two heat sink streams. Stream number 3 and 4. Stream 3 wants to be heated from 80 Celsius to 120 Celsius, and stream 4 wants to be heated from 50 Celsius to 220 Celsius. So you can see you have two hot streams, two cold streams. So if you want to design a heat exchangers to match these streams together, how do you do that? That's why we have to build our tools before we decide to select the heat exchangers. As I said, one of the tools in pinch analysis is making composite curves or cool composite. If you look at the graph here on the top left, so before I say that, composite curves are diagrams that represent whole hot streams and one diagram that represents whole cold streams in one place. And that diagram usually has its y-axis is temperature and x-axis is energy, is heat. Okay, so back to this case study here. If you plot those streams in terms of temperature range and energy and the energy that they need to lose to be cooled down. So this is the stream 1 from 200 to 100 Celsius, and stream 2 wants to be cooled down from 150 to 60. If you see, by plotting these two streams in this diagram, you can see that these two hot streams, they have overlap here. Okay, so what you can do, you can combine them. You can combine them so that this intermediate can be represented by one stream with the total heat capacity of 60 as shown here, because the stream number 1 has a CP of 20, stream number 2 has a CP of 40, so this intermediate stream should have a heat capacity of 60. Okay, for that range of temperature, from 150 to 100, for example. So by this kind of combination of these two streams, you make one stream, only one stream that represents the two hot streams. Similarly, you can do it for cold streams. So you can see that the stream number 3 and stream number 4 are shown in the on the temperature enthalpy diagram on the left bottom corner. And again, you can see that these two streams, they have overlap here. In fact, stream number 3 is completely overlapping with the stream number 4. So if you combine these two streams at this interval, you end up with a new stream with a CP of 95. Okay, so by this kind of combination of cold stream and hot stream, you end up with two composite curves. One composite curve that represents hot streams, one composite curve that represents cold streams. Okay, after you do that, after you match up these streams, after you make the composite curves, then you show them, you draw them in one graph only. Okay, you draw them in one graph. So like this graph shown here, you can see that hot stream is the red one, and uh, cold stream, cold stream uh, is, can be shifted to the right or to the left as long as the initial temperature and the final temperature of its composite curve doesn't is fixed. So you have the hot stream and then you have the cold stream. You want them to match together. Okay, you switch back and forth. If you see, due to the shape of the composite curves, always at one specific point, there is a difference. There is a minimum difference between uh, composite curve of hot streams and composite curve of the cold streams. And this minimum difference between the two uh, composite curves, we call it delta T mean. Minimum temperature between uh, hot stream and cold streams. And that point is called pinch point, that is shown here by Pensman. It's a pinch point. Okay, so the reason that it is called pinch is now clear. So when we say pinch, we are talking about the narrowest interval or the narrowest temperature difference between the hot streams and cold streams in the process. Okay, that's why we call it pinch point. And usually we call this delta T mean. Usually this delta T mean has a value around 10 or 20 Celsius. But the question is, what is the real value of the delta T mean? So uh, you are matching hot streams and cold streams like the figure that we have here. Okay, so by this matching, always as we have shaded with the gray color, um, there is a kind of overlap between hot streams and cold streams, so that the heat from the hot stream can be transferred to cold streams. Okay, and also yeah, this overlapping zone is the zone that you have to design a heat exchanger, because this is really the zone that heat exchangers are used. But if you see, we have two other zones below and above this overlapping zone. The lower zone is the zone that you have hot stream uh, hot stream composite curve, but underneath there is no cold stream. In other words, you have some excess of hot streams, uh, but they require something to lose their heat. Here, so that's why for this as a part, you have to use a utility like cooling water to cool down this part of the hot streams. And for the upper part, you see that you have a segment of the cold composite curve, which is not overlapping with the hot streams. So this part requires a utility like a vapor, for example, in order to be heated. So again, you need to design a, a heating utility, a heater in general, in order to um, in order to heat up the remaining part of the cold stream. But there are a lot of discussions here. So if you pay attention to the curve carefully, I said this gray zone is the zone that you have to use for heat exchangers, because this is the zone that process cold streams and process hot streams are overlapping. So this is the zone that you have to design heat exchangers. But if you, and let's say, for example, for this case, this delta T mean is 10 degrees, 10 degrees Celsius. But if you switch, for example, the cold stream to the right, okay, if you switch it a bit to the right, you can see that this overlapping zone will be less. Okay? You will have less overlapping zone, and consequently, you will have larger requirement for utility cooling, or like a utility cooler, and larger zone for utility heater. So by just shifting one composite carafe relative to other one, you know, you can have uh, higher utility or less utility. In other words, you can have higher heat exchanger or less heat exchangers in the overlapping zone. But the thing is, this overlapping zone, okay, this overlapping zone is a matter of uh, uh, capital cost. Because if you remember, we said when you design a heat exchanger, the equation is overall heat transfer coefficient multiplied by heat exchanger surface area multiplied by logarithmic temperature average. So you need to design heat exchangers to supply this surface area that you want. So if you, in other words, if you have very small very small delta T, very small delta T mean, or very small pinch point, your overlapping zone will be maximized, and so you will have more heat exchangers. And on the other hand, if you increase your delta T, if you increase pinch point, for example, from 10 degree you switch to 40 degrees C, okay, you of course you will have less, you will require less surface of heat exchangers. On the other hand, you need more vapor to heat up your cold streams, for example, and you need more cooling water to cool down your hot streams by utility. Okay, so this is kind of trade-off. That's why uh, you have to do optimization work. So people who design heat exchangers by pinch analysis, they design, I mean, they generate the kind of cost, technical and economic cost analysis tool, techno economy assessment tool, or TEA, techno economy assessment tool, or T. They design this kind of tool, and then they evaluate the total cost of the heat exchanger network. Uh, so you will see, as shown by this graph on the right, if you increase the delta T mean at the pinch point, you will have less capital because overlapping zone is smaller, so less heat exchanger is required. But energy consumption from utility part will be higher. So at the end, uh, by estimating the total cost of the heat exchanger network, you can obtain the optimum delta T, which is associated to the point where the total cost is minimum. So the best way is to find the delta T mean is to do a kind of optimization to where the total cost of the heat exchange network is minimum. But I have one question. I want somebody to answer my question. Is it possible that delta T mean at the pinch point could be zero? So that, for example, you have, let's say, one graph like this, you have one graph like this, for example. So the two composite curves completely match, so that you have one zone here and you have one zone here. Two distinguishable overlapping zone. Can we have the 30 mean equivalent to zero?
Uh, yes, you can, but you should use a heat exchanger with infinite area.
Exactly. So it means no then. Yes. Yeah, exactly. If you again, Q is UA delta T, So if delta T is zero, it means area should be infinity. So you have infinity size of the heat exchanger. So therefore, delta T can never be zero in pinch analysis, in thermal pinch analysis. Okay. Pay attention because next stage when we are talking about a water pinch, it is different case. Now we are talking about thermal pinch analysis, and delta T can never be zero. Okay, this is one criteria. Another criteria in pinch analysis is when you design a pinch, you should never assume that heat. Imagine that this is the pinch zone, pinch point. You should never assume that the heat from the upper part of the hot streams can be transferred to lower part, okay, and vice versa. From the lower part, you can transfer heat to here because uh, thermodynamically is not possible. Okay, so when you say pinch point, you really specify two distinguishable overlapping zones: upper zone of overlaps and lower zone of the overlaps. Okay, in other words, when you want to design, uh, let's say you have a couple of hot streams, you have some hot streams and you have some cold streams. Okay, always, always you have to show, uh, you have to identify the pinch point. Okay, uh, so if you are interested to learn more about details, please see the references in the Moodle. So first you have to identify the pinch point, and then uh, design your heat exchangers. In other words, always the cold and hot streams on the right, they can match together, and hot and cold streams on the right can match also together. In other words, if you design a heat exchanger that is matching from the left side of the pinch to the right side of the pinch, if you cross the pinch point, is not acceptable, it's not possible. Okay, so there are details in pinch analysis. But anyway, this technique of pinch analysis is extremely important in order to uh, maximize the overlap between the process streams, so you can maximize after this total cost optimization and minimize the utility consumption, minimize consumption of cooling water, electricity, if you are using, for example, electrical heater or boiler, whatever, in utility part. Just an example here. Uh, this is a process flow sheet. for a biorefinery process to produce furfural. So furfural is produced from one stream of coming from pre-hydrolysis step, and it goes through a couple of heat exchangers and filters to remove some undesired materials, and then you have a reactor where you have the conversion of sugars, and again another heat exchanger here, then two distillation tunnels. Eventually you make furfural. In this process you produce almost 47 ton per day furfural from the total I can say inlet stream of almost 5,000 ton. Okay. This process, if you see in here, after process simulation, for example, by Aspen, we figured out that there are some parts of the process that we have streams that they require energy. We can show them by red color. So these are heat sink streams. And we have some streams that they need to be heated. Okay. Sorry, they need to be cooled. So they are heat source streams. For example, at the beginning, we need a heat exchanger number one, in order to cool down our stream before getting into filters. So we have there are a couple of parts of the process that there are heat sinks at heat sources. Okay, if you match up these hot stream and cold streams to make your composite curves, okay, you end up with this kind of curve that you see. You have one composite stream, composite hot stream, and one composite cold stream. If you pay attention to this curve, there is a misleading part. Is the pinch point, right? It means if you want, this graph shows that. This graph shows that the two composite curves are really touching each other. As I said before, this is not possible. That this is associated with infinity size of the heat exchangers. But this is just to show you that if you completely pinch your composite curves, this is the minimum heat that you need from the utility heaters to heat up your remaining cold streams, and this is the minimum cooling utility coolers that you need to cool down your remaining hot streams. Okay, this is the minimum that you want. But of course, there has to be a optimization tool to find what is the delta T minimum here. Okay, to find it. So this work has been done by a PhD student a couple of years ago. The PhD thesis exists in Moodle. You can go to see the literature. But the message is here. That PhD student assumed delta T could be 10 degrees per minute, but I completely disagree that you just assume something because maybe it's completely wrong. There should be optimization tool. Apparently, he didn't have that optimization tool. He assumed delta T of the total network could be 10 degrees C. And then he evaluated his cold stream and hot streams, and he figured out that, for example, by looking at the condenser on top of the first distillation column, part of the heat that has been released after condensation can be used in order to preheat, can be used in this heat exchanger, okay, in order to preheat this stream and have it to 61 degrees C, okay, and also part of the energy from this stream here can be used from this stream in the exit of the reactor number 1 can be used to preheat the exit of this exit stream of this one in another heat exchanger in order to have this input stream into 139 Celsius. By this kind of just analysis of heat source and heat sink by after process simulation and just kind of auditing of how what heat sink can be matched with one heat source, he identified that he can really apply a significant energy saving in the process. But for example, without doing any heat integration, the total energy that was required for heating was 14.2, but by this kind of heat exchanger heat integration that he made, the total required heat was decreased to 11 megawatts. And vice versa, the energy for cooling from almost 26 megawatt was down to almost 23.5 megawatt by just this simple heat integration. So if you want to do heat integration, what you have to do, let's say you are doing your process, your process course, your process design project. First, you have to do a process simulation, for example, in Aspen, and then you have to identify where you have where you have heat sinks and heat source. Then you need to design. You need to decide if it's better to have process-to-process heat exchangers or utility heat exchangers by simply pinch analysis method. Okay, and then you will see that you can really minimize the energy consumption of your process. So this was the thermal pinch analysis. I'm going to give you 5 minutes break and then we continue our discussion on water pinch.
J'avais une petite question.
Yeah.
Je voulais savoir, c'est quand vous alliez corriger les examens?
Good question. No, not yet. I will send you by Saturday. I didn't finish it, unfortunately. There was a proposal deadline that I had to finish. Unfortunately, I couldn't finish, but you will have it by this weekend. Saturday.
Okay, merci.
Any other question? So what happened? Almost 4 people left. More people are leaving. Okay, so I have one question. So maybe somebody can answer me. What is pinch analysis?
Using energy of some units to other ones to cooling down some streams to and heating up some other streams. It decreased the cost of all process. That's it.
Yeah. So I think the better answer could be pinch analysis is so let's say thermal pinch analysis is a heat integration tool to maximize process to process or to optimize process to process heat exchange so that you will have minimum consumption of utility. So utility could be coolers or heaters. But okay, what good answer. So maybe I can ask also somebody when we talk about utility, what is utility in a process?
Each stream that comes from outside the process, when it's hot or cold, is utility.
Like what? Yes, but some example?
Like hot oil, water, steam, low pressure and high pressure, refrigeration, and sometimes in cooling we have ambient temperature. We can use ambient temperature. We can design pinch analysis based on ambient temperature in that area.
Okay. Maybe I ask somebody also a very tricky question. Do you think a combustion reactor is in a utility section or in process section?
I think that is part of the process.
Who answered that?
I think that if it's be a part of process, it's not utility. It's part of hot stream. You can extract. A reaction occur in the combustion and produce heat, and you can use this heat as a like this. It's not utility.
Actually, Professor, I think the main goal of combustion reactors are producing heat to producing energy. So it is the main process, not the utility process.
Okay, so think about it. Okay, I will ask it maybe as it is on Tuesday, but it's very important question. Just to give you a guideline, is you have to see what is the purpose of combustion. But please keep in your mind that it's a very important question. If the combustion is a utility part of the process or the core part of the process. Okay, so now we are talking about something also very interesting that is called water pinching. Water pinch or pansement echo. So also it's called water pinch. Why water pinch? Because as I said, water is interesting stream in any process. Water is a utility stream. Also, it is a stream that is part of process streams. Okay, so it is important to also have minimum water consumption. If you remember in the in pinch part, for example here, for this part, if you want to cool down your hot stream, how do you cool it down? Either by air fan or by cooling water. Have you seen cooling towers in refineries or power plants? They use water cooling towers. Of course, sometimes air fans are used, but cooling water is very known. Okay, but water is, as I said, water is also uh, uh, a process that is produced in the stream, and this is why it is important to, also have a very interesting integration of water consumption, because maybe, for example, for here, part of the water that you need could be the water that you produce in the process. It doesn't have to be the fresh water from, let's say, city or from well, from somewhere, So it is very important that, therefore, it is very important that we have also an optimized network of water system. In fact, a pinch methodology, a pinch analysis started from thermal pinch analysis, but nowadays is used for even hydrogen consumption. You know that hydrogen, for example, is used in the process, but also hydrogen is produced in process. So there are the pinch analysis, something very interesting. But there are some differences and some similarities between water pinch or pinch-mo-aku and thermal process. Can you guess? Can somebody tell me what kind of similarities could be between water pinch and thermal pinch? Okay.
Maybe we have also a pinch point for water pinch, and we have something like utility. I mean, water from outside the process. We need this like utilities.
In other words, it's better to say in both we are talking about supply and demand, sink and source, or source and sink. We have a group of streams that they need energy, or we have a group of units that they need water. Okay, and also we have a group of streams that they need to lose their energy, and also we have a group of units that they need to discharge their water. So we have always, so similarity is the idea of supply and demand, sink and source. Okay, but there are still similarities while there are differences. For example, so these are the two streams, two similarities, but the difference is that, for example, in water pinch, in water pinch, we are talking about purity or concentration of the water stream. It could be water, in general, we can call it aqueous stream, because it could be kind of effluent that has water and a lot of impurities. But when I say water here, I'm not talking about clean water. We are talking about a stream that has significant mass of water. Okay, otherwise you can call it aqueous stream. So in the water pinch, we have purity. We are talking about purity, while in thermal pinch we are talking about temperature. In our curves, if you remember, we had temperature versus we had Q. Okay, but in water pinch, we have purity or concentration versus flow rate or dB of water. Okay, so this is the term in. I prefer to show it by like a watt presenting energy, but in water we are talking about mass flow rate, for example, kilogram per hour. Okay. Okay, good. I was worried about my laptop. So an example here. Imagine that you have one stream of paste in a pulp and paper company. Okay, and that stream is supposed to undergo kind of washing or kind of dilution. So if you want to wash it, you need water. So you can have, for example, clean water to apply your washing or dilution to remove some impurities, for example. Okay, so after that, the material, your system of dilution has to undergo kind of filtration by press, for example. So and eventually you have one aqueous stream, we call it filtrate. Okay, and this filtrate contains a lot of water, and also in the solid phase you have washed paste. So by just these two steps of washing and filtration, you can see that in washing you are demanding water. You are demanding. So here is demand, but here after filtration, since you do filtration, the solid is separated from water phase or aqueous phase. Here you have supply or source of water. Okay, so I hope you understood how we can have water demand and water supply in the process. So imagine that now, similar to thermal pitch analysis, you can define also composite curves for water streams with respect to purity or concentration. Talking about concentration, it depends on the material of interest. Let's say whatever concentration. So in water stream, you can find out several streams that have similar purities, and by combining them, you make this kind of composite curve, S1, S2, and S3. So each one has specific purities with a total flow rate. Okay, and you do the same thing for demanding water. Okay, so again, depending on the concentration of the streams, you can combine those type of water streams that have similar purity or concentration, combine them in the purity versus flow rate curve. Okay, and after you make these composite curves, you can combine them. But if you combine like the figure that now I will show you, this is not a good idea. Why? I think Ahad today is very active. Ahad, can you tell me why this kind of combination is not good between demanding and source of water?
There is two pinch points. Pinch.
Okay, in fact, there are 3 pinch points. One is here, one is here.
Yeah.
3.
Yeah, but the problem is, Here, your demand is higher than your supply. It should not look like that, you know. The supply should be on top of the demand, you know. So it doesn't work like that. So what you have to do, you have to end up with the curve like this one. So you have to match up your composite curves of water. Curves of, I can say, water composite curves, so that it makes sense. Because you cannot have for example, in the case of here, you cannot have demanding water with a higher concentration for a supply that has lower concentration. It doesn't make sense. Okay, from mass balance doesn't work. So you have to put them into this configuration. So, but by looking at this curve, then you can see that always these supplies, these supply streams, they can supply the water for these units that they need water. So you can have again, you have this kind of overlapping for water pinch. And by doing so, similar to thermal analysis, you end up with two overshoot units, zones. One zone is for here, so you end up with a kind of OUZ or wastewater. So you have just a wastewater, and for this zone, you need fresh water to supply the water for streams D3. Okay, so you can do like that. But if you pay attention, the pinch point is here, but the pinch point here is like zero. I mean, they are just touching each other. It's okay. In water pinch is okay. In thermal pinch doesn't work, because regarding heat exchange equation, it theoretically means a huge mass of huge size of heat exchangers. In water pinch, they can match up, they can touch. But the point is something else. If you look at this diagram on the right, you see that still looks like quite a significant amount of fresh water is used. Okay, significant fresh water is needed for D3. Okay, but maybe we can do something so that the requirement of fresh water can be less. What can we do? We can do a couple of things. One thing is like what I'm showing you here. If you mix S1 and S3 a little bit together, okay, so that the concentration in S1 increases and concentration in S3 decreases. So in fact, you end up with this zone here. So you make a kind of step here. Okay, so then by doing so, you can shift the D3, the demanding composite curve to the left a little bit. Okay, by doing so, this zone where you require more fresh water will be less. Another option is you don't need to mix S3 and S3 and S1. You can just apply kind of wastewater treatment to S1, so that concentration of S1 can, for example, the purity of S1 can increase, so that and you make this step here, and then you again push to the right to make to make less water, fresh water requirement. But here I have one question. Which one do you prefer? Do you prefer to mix stream S1 and stream S3 like the one on the left, or you prefer to keep stream S3 as is, but then add kind of water treatment to purify stream S1 and then optimize the water consumption. Which one do you suggest? Muhammad Khajui, can you answer?
I really like water treatment, so I will choose the part what it needs the water treatment.
Okay, between these two diagrams, which methodology do you
I
like?
prefer the right one.
Why?
Because this is I think this is the less energy demanding.
I think
The left one is better.
We have more
I think
supplies.
the left one is better because of the level of purity in the S13, and for example, in the left one, the level of purity in the S13 is lower than S3. The left one, I think it is better.
But the flow rate is high, so I need an equipment more robust.
We
I
should
don't know.
make a trade-off between.
Okay, good. Thanks for your answers. Again, the best answer is optimization. Okay, the best answer is to optimization. We have to optimize the process in terms of technical viability, environmental issues, and economy. Okay, economy. So why I'm saying optimization? Because both of them have advantages and disadvantages. In on diagram on the left, you are not doing any wastewater treatment. You are just mixing two streams. Okay, so in terms of capital cost, is less expensive than the diagram on the right, because applying wastewater treatment on S1, it means that you have to build the water treatment utility, right? So it costs you. But on the other hand, if you look at stream 1 and stream 3, in reality, maybe these are two streams that if you mix them, first of all, they are at different temperatures. Okay, so if you mix them, maybe the final mixing temperature is not appropriate for the process. So far we didn't talk about temperature of water streams, but in fact, each water stream can have different temperatures. Maybe one stream is toxic, one stream is not toxic. So toxicity of the streams is also important, right? So if you remember, if you pay attention, I mean, in water pinch, the y-axis is about purity, and we are matching each streams that have similar purities. Okay, in terms of composition of the, let's say for example contamination. So if you mix two streams together, maybe you are risking to complicating your process just by adding a contamination from one stream to another stream. So environmentally could be an issue then. Also, even technically. So see, the best answer is to understand what scenario is better to maximize supply and demand to exchange water, is really a matter of optimization. already I talked about optimization in thermal pitch analysis. As you saw, by shifting the delta T in different values, at the end, the total cost has the minimum trend and then increasing trend. I mean, decreasing and then the increasing trend. And that minimum point of the valley is associated usually to delta T that we have to take. For water pinch, optimization is a bit different. It's different because here is not based on delta T. Here the optimization is really more complex in water treatment because purity of water itself, temperature of water, and mass of water, whatever you call it, the mass flow rate, all are important so that you can make a good optimization to minimize at the end, to minimize requirement for wastewater, fresh water, and minimize production of wastewater. Because if you produce wastewater and you just dump it to environment, is not acceptable. So there are optimization methods like stochastic methods in order for reaching an optimum network of water in the process. Okay, so this is not the scope of the course, just to give you an idea that these stochastic methods that are basically mathematical modelings mostly are available, and if people are interested to work on this kind of water treatment in biorefinery or in any other process in their master or PhD projects, they can take on one of these techniques and do the job. So as you see, these programs are classified usually in three categories: mathematical programming algorithms, for example, mixed integer linear programming, mixed integer nonlinear programming, genetic algorithm, and fuzzy logic. I forgot fuzzy logic algorithms. So there are different sorts of algorithms to really optimize the network of water in the system. I don't want to panic you, so don't worry, you are not going to do it for this course. This is just to give you this information that this is the job that has to be done in a real process engineering work. But if you ask me, okay, which mathematical model, which modeling, technique should be used to optimize the process? So the answer is on this graph. Depending on continuous I don't know why my words are a bit limited. Depending on the continuous variables in the process and number of the discrete variables in the process, if you plot, then you can, based on this map here, you can figure out which technique you have to use to optimize. But if you're asking what are these continuous and discrete parameters, it's a very good question, but it is really depending on the process that you work with. But just to give you an idea, what they are, for example, if I ask you how many people are at the class, you say, for example, 15 students are at the class. So 15 students, it means this is a discrete variable, number of the students. We cannot have 2 students and 2.5 students. This is a one discrete parameter. But if I ask you what is your height, we can say I am 1 meter and let's say 80 centimeter. So see, this is the continuous variable. So it means that there are variations of that quantity between two data. So this is something that is interesting mostly for mathematicians or graduate students who work on mathematical modelings. This is just to give you impression that you have to do mathematical modeling and optimization in order to really optimize your water network. So just to wrap up the course for today, because I think the other 15 slides I have to cover it on Tuesday. I was intentionally slow to discuss one slowly so that you guys follow this important topic. So if you look at any process, for example, any biorefinery process, so you see that beside the main biorefinery process, you have an important utility process, and there is interaction between each unit in the process, specifically in terms of energy and in terms of water. For example, as shown by different arrows, back and forth arrows, you can produce some effluents in the biorefinery, and the effluent can go to a water treatment network in the utility process. You generate clean water or fresh water. Fresh water is back to the biorefinery, and the remaining is effluent. Okay, and vice versa. Or you can make steam. You can make a steam in the utility system and use the steam in the biorefinery. But also, of course, actually, this steam could have two arrows, because part of the steam also can be used, can be produced in the process. And this is really, this diagram really shows you that how a biorefinery process can be complex, because usually we put our main focus on the main process in the biorefinery. Let's say you have a specific biomass and you want to make a specific biochemical, but you should never forget that around the process you will end up with used water, some units that require water, some units that require energy, and some units that they need to release their energy to cool down for the next steps. And because of that, we have to have a very optimized process in terms of water optimum consumption of energy and optimum consumption of water. In other words, we have to make sure that as much as possible we are using process-to-process streams, either thermal or water streams, so that we will be less dependent on utility. And even though you can do this kind of integrations, heat integration or water integration, still your utility will be itself quite complex. So this is the vision that exists, and we have to really, step by step identify how to optimize our process in terms of energy and water. So I want to leave it for today. Next Tuesday we can continue the rest, but at least I want to ask you to focus, to really go through the slides, really try to understand pinch and thermal pinch and water pinch, because then it will be easier for you to follow the rest of the course.